Hey guys, today we're going to learn about collisions. Alright, now Mr. Erko, I recognize that equation. You had that up during the last video. You're right, I did, because it's the only momentum equation you'll ever need. It's always right. Momentum before equals momentum after. That's just as true for explosions as it is for collisions. So today we're going to look at collisions, but they're going to use the same exact equation. So if you write this equation down for a momentum problem, you're probably not wrong. It's going to be the correct one to use. All right, now, types of collisions. You got to know a little bit about the types of collisions. So the basic categories are inelastic and, unsurprisingly, elastic. If a collision is inelastic, what that means is some amount of kinetic energy is lost. Where did the energy go? It's so sad. All right, now where did the energy go? Well, there's usually about 3 different places where I'll say energy goes. Probably there's more, but the big ones are heat. Always heat's going to be produced. Deformation of materials kind of ends up producing heat. But deformation, all right, so if there's any like crunching of the materials during a collision, energy was lost. Third place is sound and vibrations. So sound is specifically vibrations that go through the air. Well, there's energy there. It's a tiny amount. Not very much energy is present in sound. You also have vibrations in general. So like if I throw a tennis ball at the board or something, right? It's going to hit the board, bounce off, fine. So there's going to be some deformation in the tennis ball. All right, so there's some energy lost. There's going to be vibration in the board. There's more energy lost. And then I will also probably hear something, at least like the board rattling. All right, and so there's some energy there. So those are the 3 places where energy goes when it goes away. You should know those. If you didn't write those down while I was talking, you should back up the video and make that list again, because it's an important one. Okay, now, some kinetic energy is lost if the collision is elastic. Well, I think you can guess then that means that elastic means that no kinetic energy is lost. We'll probably do more about elastic collisions in, say, another video sometime. Mostly I want to deal with the inelastic variety because, frankly, these are a lot more common. Most collisions, all collisions on the macroscopic level anyway, are going to be inelastic at least a little bit. In general, though, you can say the more bouncy they are, the less kinetic energy is lost. So the closer they are to elastic. But almost any collision is going to lose at least a little bit of kinetic energy. All right, now, let's see. If the collision is inelastic, we said some energy is lost. There's a special case here, though, where you lose the maximum amount of energy. And that's where it's perfectly inelastic. What perfectly inelastic means is they stick together. All right, well, if they stick together, that means that the 2 objects must have the same final velocity. So if you recall from the previous video when we were doing explosions, we had, the left side was lumped together. We had an m total times whatever the initial velocity was. Here we're going to have basically the reverse of that. If 2 things collide and stick together, that means that the v1f and the v2f are the same thing. And so that means that the 2 objects will move together as one. So if you like, you could say a perfectly inelastic collision is sort of like an explosion in reverse. All right, they're sticking together rather than blowing apart. Okay, so if they stick together, then this equation on the right side will have a term which looks like m total, or if you like, m1 plus m2 v final, because they don't have separate velocities. They are their own thing. All right, so if it's perfectly inelastic, the most energy that can be lost is lost. Doesn't mean all the energy is lost, just as much as could be lost during this collision. All right, so with all that, let's look at this example here. It might be example 5 or something like it in your notes packet. It says we've got, a guy on roller skates. He's rolling along, minding his own business. All right, why don't you go ahead and draw a diagram of that. So here we are with a great diagram and a great equation. All right, now if I start plugging things in here, it says the guy is 60 kilograms, so he's not very heavy. His initial velocity is 2 meters per second, just rolling along. And then here comes the medicine ball. It says it's 8 kilograms, but we don't know how fast it was moving. All right, on the other side, now, since he somehow caught the ball, instead of saying V1 final and all that, we're going to go with the perfectly inelastic collision format, because they both have the same final velocity. All right, now, M1 plus M2, that would be, looks like 68. Yeah, 68. And it says his final velocity after catching it is 0.5 meters per second. All right, now, I just made a mistake. You should pause the video and try to find the mistake, and then resume. Yes, that's right. The mistake I made is signs. If this is positive 2 meters per second, this must be negative 0.5. And if you mess that sign up, you're going to find there's a big difference in what the velocity of the medicine ball must have been. If he's drifting backwards at 0.5 meters per second after catching it, it must have been going way faster than if he caught it and just slowed down but kept on going forwards at 0.5 meters per second. Okay, so the signs make a difference. Please, please, please be careful with the signs, because if you mess those up, all kinds of answers are going to be incorrect. All right, so go ahead and pause again and see if you can get the correct answer for V2 now that you have the right sign for the final velocity. Yeah, somebody has it in for this guy. That's not safe, all right? So he's probably going to need to spend some time in the hospital. All right, now, be that as it may, I'd like to look at part C, how much kinetic energy was lost when he caught the medicine ball. All right, now, these questions about like how much kinetic energy is lost are very much for the accounting mind, all right? You have to keep track of each and every object, because if anything is moving, then it has kinetic energy, and therefore that's part of your calculation for how much kinetic energy was lost. Now, I did skip over talking about part A here, which wanted to know what kind of collision is this, and is kinetic energy conserved or not? I think the answer is obvious if I'm also asking how much kinetic energy is lost, but specifically, this would be our perfectly inelastic collision. You should be specific if I ask that question. If you said inelastic, it's yes, it is, but you can be more specific. You could say it's perfectly inelastic because he caught it. All right, so how much kinetic energy is lost is going to look like this. Delta K equals, well, that'd be K final minus K initial. All right. We know kinetic energy follows the formula 1/2 mv squared, but you got to be careful. Multiple things here have kinetic energy. Let's look at after. After the collision, it's him and the medicine ball. Okay, so that's 68 for their combined mass. Rolling along at 0.5 meters per second. Now you'll notice I dropped the negative sign. Don't include the negative sign. You're going to square it anyway, and it's only going to screw you up. Kinetic energy can't be negative, so it doesn't matter whether it's a positive or a negative number for a particular speed. All right, so that's the final energy, once I type that all in and work it out. The initial energy, though, is more complicated. If you're thinking, well, the medicine ball, that's what I'm going to do. I'm just going to do the medicine ball. The medicine ball is not the only thing in motion. Now, it is moving super fast, so it does have most of the initial kinetic energy, but the guy is also moving. So when you calculate the initial kinetic energy, you've got two things that have kinetic energy. All right, so that means your initial energy isn't just one thing, it's two things. I kind of ran out of room here, so I'll write it below. 1/2, 60, and then his velocity is 2. Okay? And so now you have to add those two together, and that will give you the initial kinetic energy. And then subtract that from the final kinetic energy, and that will tell you the change in kinetic energy. In this case, it'll be a negative number, and that will indicate the amount of energy that has been lost during the collision. Okay, well, I will leave it to you to type in the numbers and figure out exactly what that is. It's going to be a big number. A lot of energy was lost. I will talk about one more possibility here rather than type out numbers and stuff. Suppose that he had shielded himself from the medicine ball and it had bounced off. Well, in that case, you would have two different final velocities. Okay, so that would be the maximum complicatedness, right? If he is simply hit by the medicine ball, then you would have the initial kinetic energy would involve two separate things, right? Two separate terms, one for each moving object. And the final kinetic energy then would also have two separate terms in the event that it hit him and bounced off. Okay, so that would be as complicated as it would be. I would probably not give you a question like that on a test or a quiz, but just for the sake of argument, right? That's as complicated as it would get for this sort of thing. All right, I hope that was helpful. Now you know a little bit more about collisions.